Hello everyone, how are you? I hope all of you are well. So welcome in GATE 2003 one shot series. So today we are going to discuss lathe and drilling, right? Today we are going to discuss lathe and drilling. So let's start today's session. In lathe, first of all, I'm going to discuss about the lathe. You can see the picture of the lathe here. Dear, this is what? This is the lathe. A lathe is what? A lathe is a large machine that rotate the work. A lathe is a large machine that rotate the work, and the cutting is done with a non-rotating cutting tool. See, here the workpiece is going to fix in the work holding device, and the tool is going to fix in the tool post, which is mounted on the carriage, and carriage will do a linear motion. So generally tool is not going to rotate here. The cuts are generally round or helical. Generally we are produce a cylindrical surface, and generally we are produce a spherical helical surfaces like threads, right? So the tool is typically moved parallel. So the tool is typically moved parallel to the axis of rotation. This tool is moving parallel to the axis of rotation. Am I clear? During the cutting process. Now my dear, you can see there is a headstock. This is what? This is a headstock. See, this is a headstock. So what is the function of headstock? This end of the lathe, please listen me carefully. This end of the lathe, right? This end of the lathe contains the driving motor and gear. Contains the driving motor, my dear. Contain the driving motor. The driving motors and gears. The driving motors and gear, right? So here power to rotate the part from here, power to rotate the part which is fixed in the work holding device is delivered from here, my dear. This typically has some lever. This typically has levers that let the speed and feed be set. There are typically some lever. By adjusting the lever, you can set the speed which is required. Okay. Now, the next component is vase. This is vase. You can see this is what? This is vase. Now, what is vase, my dear? Here, the function of vase is along the vase, the carriage will slide. There are hardened rail. Okay, basically these are what? These are, I'm going to write, ways are what? Ways are what? The hardened rail. Ways are hardened rails. Okay, hardened rails, right? These are what? Hardened rails. That the carriage ride on. That the carriage rides on. That the carriage rides on. That is called as ways. Now at the end you can see there is a tail stalk. This is what, my dear? This is tail stalk. See here. This is what? This is tail stalk. Now what is the function of tail stalk? Basically, tail stalk, this can be used to hold the other end of the workpiece. Okay, this can be used to hold other end of the workpiece, or sometime, my dear, you can mount the drill tool or a reaming tool in the tailstock, right? you can mount the drill tool and reaming tool in the tail stalk. Am I clear? So this is basically some features of your lathe. Now let's discuss about the bed. Let's discuss about the bed. Yes, so I'm going to rub here some of things. I'm going to rub here some of things. Now I'm going to discuss about the bed, right? Now I'm going to discuss about the bed. See please. My dear student, here you can see this is bed, right? This is what? This is bed. See here. This is what? This is bed, right? This is what? This is bed. So bed. This is the bottom pin of the lathe. This is the bottom pin of the lathe that carries chips and cutting fluid, right? Bottom pin of the lathe bed, okay, carries cutting fluids, carries cutting fluid and chips, okay, and chips, etc. Sometime it will absorb the vibration which is going to be produced, right, in the machining, right? You can see here carriage is there. This is what you can see, a carriage. My dear, carriage will do a linear motion. Carriage will do a linear motion, and the linear motion of the carriage, basically on the carriage, a tool post is going to be what? A tool post is there, and in the tool post we are going to mount a tool. So this part of the lathe carries the cutting tool. This part of the lathe carries cutting tool and moves, and the linear motion moves based on the rotation of the lead screw, okay, or lead rod. Here you can see, my dear, there is a lead screw. Are you able to see? This is the lead screw, and this is what? Lead rod, right? This is what? Lead rod. Basically what happened, my dear student, here we are going to supply the power. We are going to supply the power from headstock either to the headstock, okay, or either to the your lead screw, right? Either to the lead screw. There will be a gearbox, right? There will be a gearbox like this, and the power is going to supply, and the power is going to supply to the lead screw and lead rod, and on the basis of rotation of lead screw or on the basis of rotation of lead rod, the carriage will do a linear motion. The carriage will do a linear motion. Am I clear? My dear, if you are talking about the lead screw, this is what? A lead screw. On the lead screw there will be a acme thread. On the lead screw there will be what? There will be a acme thread having an angle 29 degree for easy engagement and disengagement. Having, this is a acme thread of 29 degree. Why? For easy engagement and disengagement of the half nut or of the nut which is present in the carriage, Am I clear? So on the basis of rotation of lead screw or lead rod, the carriage will do a linear motion, right? Here the workpiece which is going to be mount here. Let's say this is a workpiece which is going to be mount here. Here workpiece, my dear, will do what? Will do a rotation n, okay, revolution per minute. So the critical speed, here, the critical parameter on the lathe are speed of rotation. Generally we take a RPM. Whenever you talk about the cutting speed, basically you're talking about the RPM. You can find out the speed also if you know the diameter of the workpiece. If you know the diameter of the workpiece, then how can you find the cutting velocity? Cutting velocity equal to pi diameter of the workpiece rpm divided by d is in mm, so 1000 meter per minute. That is a cutting velocity which is depend on the number of rpm if the dia of the workpiece is what? Dia of the workpiece is fixed, right? Dia of the workpiece is what? Dia of the workpiece is fixed, right? Okay, now here I told you that all the gear we have seen in the last slide, that in the head box basically all the power delivering, okay, all the motors basically here all the motors are there, right? This is a motor or a gearbox, right? This is a motor or let's say a gearbox, right? So this is what? This is a motor, right? I hope it is visible. Okay, this is what? This is motor, this is the motor, this is motor, and this is what? Gearbox. So motor will deliver the power to the gearbox, right? And gearbox will deliver power to the work holding device, a work holding device which is called as what? Chuck. There will be a different work holding device. Let's say this is what? Chuck, C-H-U-C-K. Chuck basically used to hold the workpiece, right? Chuck basically used to hold the workpiece. So this is your workpiece which is going to be held with the help of chuck. Chuck may be a 3-jaw chuck or 4-jaw chuck. We will discuss later. Here, what I am trying to say, that the motor is going to deliver the power, right? So this is a motor to the gearbox. Basically, my dear, by using the gearbox, you can manage the speed that is RPM. So the number of spindle speed is a geometrical progression. Suppose that the minimum RPM which you can produce from the gearbox is what? Suppose that the minimum RPM which you can produce from the gearbox is what? Let's say the number of RPM which you can produce from the gearbox, let's say N1, right? Let's say N1, this is a minimum RPM. The next speed which you manage by adjusting the lever on a gearbox will be what? Will be N1R. The next speed will be N1R square. So the number of spindle speed, the number of spindle speed is in a geometric progression, is in a geometric progression. Am I clear? Is in a geometric progression. It will go N1, it will go N1, okay, R to the power small n minus 1. What is a small n? Small n is the number of spindle speed. Suppose that you need a 6 speeds in your car. There will be a 4 gear, there will be a 5 gear, there will be a 6 gear. That are what? That are number of speed, number of gear which you can, okay, which you can apply, according to which you can increase your speed. So small n is a number of spindle speed, okay, is required with capital N1 is the minimum speed, right? Capital N1 is what? Capital N1 is the minimum speed. So a very famous question will be asked that the number of spindle speed is in a number of spindle speed is in a GP, geometric progression. Very important, very important, very important, right? Is in a geometric progression, where you can see a small n1 will be the minimum RPM, and this, my dear, this, okay, this, please see, this, that is n1, last n1 small r to the power small n minus 1 is what? Is the maximum RPM. Now in this GP, basically R is what? R is the step ratio. The question is, how can you find the step ratio? How can you find the step ratio? Very easy, my dear. before starting the machining, before starting the machining, you have calculated, my dear, you have calculated that the required minimum RPM, minimum speed or minimum RPM is what? N1. You know the maximum, speed, you know the maximum speed, even you know how many number of spindle speed. Okay, you know number of spindle speed. You know how many number of what? Spindle speed. Then how can I find the step ratio? Step ratio, my dear. Step ratio basically that is represented by small r is going to find out by n max divide by n min 1 to the power small n minus 1, So now suppose that let assume you know the minimum RPM, right? Let assume you know the minimum RPM. Let assume that you know the minimum RPM. Let N1 will be 100 RPM. Let N max, that is what? 1000 RPM. Right? The number of speed, that is small n, you need what? 6. You need 6. So the step ratio is 1000 divided by 100, 1 to the power 6 minus 1. Right? So this 0, this 0. So here 10 to the power 1 divided by 5, it comes 1.584. My dear, this is what? This is the step ratio, right? And again a student will ask, sir, how can I find n? My dear, the minimum or maximum diameter will be given you na. The minimum and maximum diameter will be given you. Okay. A student will ask to me, sir, how can I find the spindle speed of rotation? Okay. The spindle speed of rotation. Spindle speed of what? Rotary motion. Rotary motion. Spindle speed of rotary motion. Sir, how can I find? Very simple. My dear, we know that velocity equal to pi d n by 1000, right? In journal. So what is n? N is what? V 1000 divided by pi. Divide by what? V into 1000 divided by pi d. Means if you need n minimum, then you need V minimum, right? Divide into 1000 divide by pi. D should be what? Maximum. Am I clear? If you need n max, then your velocity should be what? Max into 1000 divided by pi. Your diameter should be what? Minimum in this case. That RPM you will get. Once you get the n min or n max, you will get what? You will get the step ratio if you know the number of spindle speed. Am I correct? So D is the maximum diameter where D max, maximum diameter of job. D min, minimum diameter of job. V max, maximum cutting velocity. V min, minimum cutting velocity, right? So by this manner you can find out all the thing. Okay, now let's move to a question so that you can understand the thing in a very good manner. Suppose that here I am going to give you a question, a very good question. Let me see, a question is there. A question. Where is the question? Okay. Don't worry. I will write the question. Okay. I will write the question. Right? I will write the question. Now, see. A question was asked in 1987 GATE on this concept. A question was asked in GATE 1987, right? So what was the question? He says a 6-gear speed box, a 6-gear speed box, right, has to be designed for has to be designed for head stock has to be designed for head stock of center lathe right, of center lathe for turning of mild steel, right? Now, so the diameter are given. Okay, the diameter is given, that is the minimum and max diameter are given. I am going to write in short. So what will be the minimum and maximum diameter? That is what? 100 mm and 200 mm. The Vmax or Vmin or Vmax is given. Vmin and Vmax is given. What is that? Vmin is your 40 meter per minute and Vmax is 120 meter per minute. This is given to us. Okay, a 6 speed. So here small n is given to us. Small n is given to us. That is what? 6. Right. So what should be the values of those? What should be values of those? Of what those? What should be the values of those 6 spindle speed, right? What should be the values of those 6 spindle speed? So the basic criteria is that solution. We should find n min, that is Vmax into 1000 divided by pi d. Sorry. Here it Vmin and Dmax, right? So what is V minimum? That is 40 into 1000 divided by pi Dmax, that is 200. What will Nmax? That is Vmax 1000 divided by pi Dmin. So Vmax is 120, 1000 divided by pi Dmin, Dmin, that is what? 100. Now Nmax, N minimum and maximum. So 40 into 1000 divided by shift pi into 200. So it comes 63.66 RPM. Right. So here 100 and 120 into 1000 divide bracket shift pi into what? 100. It is coming 381.97 revolution per minute. So now you have a maximum and minimum RPM, right? Now you have a maximum minimum RPM. Now find out the step ratio. Step ratio is what? N max divided by N min to the power 1 divided by 6 minus 1. So R N max, that is 381.97 divided by 63.66, 1 divided by 5. So answer, so yes, so answer divided by 63.66 to the power 1 divided by 5. So here R comes out 1.43, right? This is what? This is the value of what? R. Now once you have the value of R, so N1 R is square, right? N1 R cube, N1 R 4 and N1 R 5. How many? 1, 2, 3, 4, 5, 6. So N1, you know the N1, that is 63.66. Now 63, right? 63.66, right? Into answer, right? So it comes 91.0, okay, 9, right? Into 1.43, okay, to the power now 2, 130, 130.17, right? Now to the power 3, 186.155. Now to the power 4, 266.20, right? Now to the power 5, 380.66. So 381 point something. So nearby it is coming. So these are all 6 spindle speed, right? So maybe the in upcoming gate exam he will ask only 1 RPM, right? And it could be any one of them. Now suppose that you are cutting a thread. So basically in thread cutting operation, what is a major requirement? Suppose that this is my work holding device. My dear student, please note down that. Suppose that this is my work holding device. This is my work holding device, right? Let's say this is my work holding device. This is my work holding device, and on this workpiece I have to produce what? I have to produce a thread, right? I have to produce a thread. See, I have to produce a thread. Right? Like this. This type of thread I have to produce. This type of thread I have to produce. Right? So these are the thread. So according to this, the tool basically will be look like this. The tool will be look like this, and this is your tool post. This is your tool post. This is the desired pitch. This is the desired pitch of the workpiece, right? And this is the tool. This is tool post, right? And this is what? A carriage. And in the carriage there is a lead screw. There is a lead screw. And you know, in the lead screw there is a Acme thread. In the lead screw, you know, there is a Acme thread. So lead screw have its own pitch, let's say L, right? Lead screw have its own pitch, let's say L. So my dear, to cut the desired pitch P, okay, the tool should move according to the workpiece. Okay, according to the workpiece, that much length tool should be, okay, move. So P is the pitch, NS, basically NS is what? NS is the RPM of the spindle or workpiece, and here this NL is RPM of the lead screw, right? And ZS is the number of, okay, ZS is what? The number of start, ZS is number of start on screw, on thread, okay, on thread. And here ZL, number of start on lead screw, NL is RPM of the lead screw, L is pitch of the lead screw, right? Pitch of the lead screw, I will write there. L is pitch of the lead screw, pitch of the lead screw, right? And ZL is number of start, and NL is speed of the lead screw, RPM of lead screw, So to cut the desired pitch on the workpiece, the relation should hold good, otherwise the desired pitch is not going to be produced. That is what? That is NS into P, ZS equal to NL, okay, equal to NL into L into ZL, right? ZL. So this is a desired equation which the tool and workpiece has to follow during threading operation. Otherwise, the desired thread are not going to be what produces. Otherwise, the desired thread is not going to be what produces. Now the question, this type of question may be asked in your GATE exam. A single start thread of pitch 2 mm is to be produced. So we have to produce on what? On the workpiece. So single start means your ZS equal to 1, pitch is what? Pitch is 2 mm to be produced on a lathe having a lead screw with a double start, that is ZL equal to what? 2 of thread of pitch, that is L equal to 4. The ratio of the spindle speed, the ratio of the speed between spindle, that is what? NS, and lead screw, that is what? NL. You have to find NS by NL. My dear, you know NS into pitch into ZS equal to NL into L into ZL. So you have to find what? NS by NL. So L into ZL divide by P into ZS. So L is what? L is 4, ZL is what? 2, P is what? Pitch, that is the pitch of the workpiece, that is 2, number of start is what? 1. So it comes 4 divided by 1, that is 4 is to 1. Answer is what? D, right? Answer is what? D. Now next is a facing operation. Here you can see in the turning operation, this is basically threading or turning. Suppose that you are doing a threading operation. Here you can see that in the threading operation, the tool will move, okay, the tool will move along the axis of rotation. Even if you are doing a threading operation or turning operation, the tool will move along the axis of rotation. But my dear student, if you are doing a facing operation, then here tool is going to be moved. From the outer periphery to the center, right? So let me draw a figure. Suppose that we are doing a facing operation. This is a cross-sectional area of the workpiece. this is the central line, right? Now see here, this is the tool. Now if the workpiece is rotating with rpm n, right, and this is what, this is the diameter of the workpiece, that is d. Now the tool will move across the face, right, that is the feed in mm per revolution. So sometime will tool come here, sometime tool come here, sometime tool come here, and at the end it comes here, right? Now the interesting fact which I am going to tell you here, the cutting velocity v equal to what, pi d n divided by 1000 meter per minute. My dear, at the periphery the diameter is what, maximum. So at the periphery the velocity is what, maximum. Suppose that if you come here, then the velocity goes decreases. Suppose the tool comes what, the tip of the tool comes here, then the diameter goes reduces, then again the speed is going to what, decreases. So here the speed is going to decrease basically. If you reach at the center, then the speed is going to be what, cutting speed is going to be what, 0. So you can say that v is directly proportional to what, dia, right, if the rpm is what, constant. If n is what, constant, n is not going to change, then cutting velocity is directly proportional to what, the diameter, right, the diameter. So here v is going to be changed linearly. Now, so this is a facing operation. I have discussed you the very interesting parameter. Now let's discuss about the work holding device. My dear, work holding device, basically the work is going to be held, okay, in the lathe. There will be a 3-jaw chuck. 3-jaw chuck basically a self-centering chuck. 3-jaw chuck basically a self-centering chuck. Okay, here the disc type of workpiece, here disc type of jobs being held in the chuck. Next is 4-jaw chuck. That is a independently adjustable chuck. That is a independently adjustable chuck, right? Here also we can hold a workpiece which are axial symmetrical, right? Along with the disc type workpiece, you can hold axial symmetrical, right? Axial symmetrical. Now collet is what? Collet basically held in a collet, a cylindrical rod like job being held in a collet. Let me show you the collet. Let me show you the shape of the collet. Now see here, a collet. Where is the collet? This is a 3-jaw chuck, a self-centering chuck. 4-jaw chuck, teeth are independently moved. And let me show you the collet. This is a collet. A cylindrical type of job is going to be held in the collet. This is a magnetic chuck. The face is the magnetic face is there. So a cylindrical workpiece whose length is small means that cylindrical workpiece is thin in shape. A cylindrical workpiece, suppose this is a cylindrical workpiece. Now see, the height or the thickness is what, is very less. So that type of face is going to be what, hold in the magnetic chuck. The next is faceplate. My dear, any complex workpiece which are not able to mount in your 3-jaw chuck, in your 4-jaw chuck, in your magnetic chuck, in your collet, even there is one more work holding device that is known as your mandrel. Okay, that is known as mandrel. So if any workpiece which are not able to mount these work holding device, then we will use a faceplate. You can see here, this is a basically you can see here, this is a faceplate. Basically on a faceplate sorry this basically on a faceplate there will be slots. These are the slots. Okay, slots. In these slots we are going to hold a workpiece with the help of what? Your clamping pin, your clamping bolt, or holding or clamping bolt, right? with the help of clamping bolts, we are going to hold the workpiece with the help of the slot which is available in the faceplate. So any complex shape is going to be held in the faceplate. Now, apart from the faceplate, there are some other type of work holding device, and let me show you some other work holding device. Basically, my dear, on a lathe center, work to be turned between the center, must have a center hold drill. Whenever you are going to hold the workpiece with the help of live center and dead center, on both the end of the workpiece you have to make a small small hole, so that you can hold that workpiece, okay, if you are holding with the help of live center and dead center, right? Live center, dead center. So center basically are of two type, live center or dead center. Live center basically is going to attach in the spindle. Dead center is going to attach in the tailstock. Live center basically used along with the faceplate. Let me show you. This is a live center, this is a dead center. So here you can see, my dear, in this figure, this is a dead center which is attached in the tailstock. This is your workpiece. This is a live center which is attached along with, which hold the workpiece with the help of faceplate. This is called as a dog. This is a dog. Okay, a dog give the structurally support to the live center and workpiece, right? So this is a lathe dog. So lathe dog are cast metal device used to provide a firm connection between the headstock spindle and the workpiece mounted between the center, right? So these are the some work holding device. These are rest are of two type. A rest which move along the tool on all or end, a rest which fix on the lathe, right? Why we use the rest? The question is, sir, why we use the rest? My dear, if the workpiece is suppose that if the workpiece is very lengthy, a workpiece whose length is very large. If you mount, suppose that if you mount this workpiece here from in the chuck and here in the tailstock, sometimes what happen, because of its own weight, the workpiece is going to be what? Bent. So to support the workpiece, we are going to use a rest. As I told you, it is used to support a long cylindrical job which is turned between the centers, right? It prevents the bending of workpiece which is caused due to its own weight, and vibration of the cutting force, mainly of two type, steady and follower. Steady generally fixed and follower will move along with the tool. This is steady, this is follower, which move along the tool. Okay, so we have finished the work holding device. Let's move to the to calculate the machining time, because generally in our gate exam machining time questions will be come, right? Generally machining time questions will be come. So my dear student, here in turning, suppose that D1 is your initial diameter of the workpiece which is going to be turned, and D2 is the diameter which is obtained after turning, right? D2 is the diameter which is obtained after turning, right? So let's try to find out the machining time. Now, my dear, here suppose that if you have provided the feed to the tool, which is along the axis of the tool, that is feed, right, in mm per revolution, and here your workpiece is rotating. Here your workpiece is rotating with RPM what? N, right, with RPM what? N. So let's try to find out some following parameter. The first parameter is depth of the cut. My dear, depth of the cut is very simple. That is D1, that is initial diameter, minus what? D2 divided by what? 2. You will get the depth of the cut. Now the average diameter of the workpiece, sometimes we need the average diameter. Average diameter basically D average equal to D1 plus D2 divided by 2. Cutting time. My dear, what do you mean by the cutting time? The machining time, L. Okay. Suppose that here Here, this is basically, you can see here, the tool moves from here to here. This is, let's say, a machining time, right? This is, let's say, a machining time. But my dear, tool has started its journey from here. Tool has started its journey from here. So it is not touching with the workpiece. So this is a approach distance. After the machining, if the tool will go for a over travel distance, that is what O. So the total length which is covered by the tool is A plus L plus O. Okay, so the total length covered by the tool is L, sorry, total length covered by the machining length, right? Total machining length, that is L plus A plus O. It would be, say, in mm, right? It would be, say, in mm. Now this is the total length. Now total length divided by what? Divide by tool speed, right? Divide by tool speed, Vx. That is a tool axial speed. Vx, tool axial speed. Let me show you in figure. This is the tool feed. This is the speed of tool in mm per minute. We want a axial speed of tool also, right? We want the axial speed of tool, that is what? Vx. And my dear, that Vx will come if you multiply F into RPM, feed of the tool, and RPM of the workpiece. So here you will get RPM, you will get Vx, that is F into N, that is what? Vx. So it comes in mm per minute. Right. Now if you're going to multiply F into N, and whose value is in mm per minute, so mm will cancel. It will become L plus A plus O divided by F into N in minutes. Generally it comes in minute. If you want to convert into second, you can convert by multiplying the 60. Now material removal rate, that is MRR. Material removal rate, that is MRR. So pi by 4 d1 square minus pi by 4 d2 square into tool speed, tool velocity, that is what? Your F into N. That much mm cube per minute will be come. Cutting velocity, that is pi, the diameter which you are going to machine, D, that is you are going to machine D1 diameter. So pi D1 into RPM divided by what? Divide by 1000 meter per minute, because if D is in the mm, then divide by what? Divide by 1000, right? Divide by 1000. Now let's try to solve this question, my dear. Let's try to solve this question. What this question will say? How much machining time will be required to reduce the diameter of cast iron from 120 to 160? So this is what? D1, this is what? D2, over a length of 100 mm. This is the turning length, which is total length is given. There in the question there is no approach and over travel, right? So cutting velocity is what? That is V, 100 meter per minute, and feed, that is given to us F, right? So you have to find how much machining time. Okay, for a machining time, you need the total time total length divided by what? Tool velocity, right? So this is LT divided by what? F into N. We have the feed, but we don't have the value of N. So what we do? We know that the cutting velocity, that is pi dn divided by d1 n divided by what? Divided by 1000. V is given to us, that is what? 100, right? So pi d, that is d1, that is 120 into n, divide by what? Divide by 1000, equal to 100. So we are going to calculate the RPM. Okay, 1000 into 100 divided by shift pi into 120, right? So here RPM will be 265.25 revolution per minute, right? Revolution per minute. Once you know the value of RPM, So the machining time will be, that is LT, total length is 100 mm, right? Divide by your feed is that, feed is up 0.2 into RPM is 265.25, right? That much minute, okay, time will be come. So 100 divide by 0.2 into answer, okay, 1.88 minute. Here the answer is 1.88 minute will be come, right? 1.88 will be come. Now the next question is a disk of, please read this question very carefully. It is a very good question. A disk of, yes, so the next question is from GATE 2013 PI. A disk of 200 mm outer and 80 mm inner diameter is phased of 0.1 mm per revolution with a depth of cut 1 mm. So let's try to make a figure of this question, right? Yes. I think it is not a cylindrical. It's okay. Don't worry. If it is not a cylindrical, we make it. Right? We make it. Because we are expert of that. So don't worry, my dear student. Yes, perfect. Right? So my dear student, here see. This is the 80 mm, this is the outer diameter, right? This is the outer diameter and this is the inner diameter, right? This is the inner diameter. So outer diameter of what? 200 and inner is 80. 200 mm and inner is what? 80. Right? 80 mm. Now, here a tool is there. A tool is there. So a feed is provided, that is 0.1 mm per revolution, which is do a phasing operation from this point, right? From this point to this point. Tool is not going to move from the outer to the center, only moving in this way, right? Now let's move. What the question is saying, the phasing operation is undertaken at a constant speed. He say speed is constant, but we have seen that speed never constant, speed vary. We have seen, remember? I show you. I told you speed is varying. See here. In the phasing operation, the speed is not constant, my dear. V is varying linearly. V is varying linearly or decreasing linearly. And he says that a speed is constant. He says that the speed is constant because here V is P is proportional to D, and every time in the phasing operation D is going to be changed. And he say V is what? V is constant. It means he is talking about V average. If V average means it proportional to what? D average. Am I clear in this question? So here he is saying that V, okay, speed that is 90 meter per minute, V average, that is a constant because average quantity is not going to be changed, 90 meter per minute, right? The main tangential cutting force is that much. Assuming approach and over travel of the cutting tool to be 0, the machining time you have to find in the phasing operation. My dear student, here the meaning of V average means it is proportional to what? D average. means you can write that V average equal to pi d average into n divide by what? Divide by 1000. Now you know the value of V average, that is 90. Now what is the D average? My dear, the D average will be 200 plus 80 divided by 2, right? Because we know the D1, D2. D average means the diameter is going to vary in the facing operation, that is 200 to 80. So 200 plus 80, answer divided by 2, 140. 140 mm, right? So 140 mm. So d pi d average, that is 140 into RPM. The RPM is not given, right? So you can find the RPM. 90 into 1000 divide by pi into 140. So 90 into 1000 divide by shift pi into answer. So it is coming 204.622 RPM, revolution per minute. Now machining time. My dear, the tool is going to be vary from here to here only. From here to here only. This is the machining length. So machining length is what? 100 minus 40, that is 60 mm. 60, right? It is what? 60 mm. That is the machining length. That is what? That is the machining length. So 60 mm. Divide by F, that is what? 0.1 into N, 204.622 minute. So 60 divided by 0.1 into answer 2.93. It is coming 2.9321 minute, right? So here the correct answer is option A. Here the correct answer is option A, right? Now, my dear, the next topic is taper turning, right? Or turning taper on what? On the lathe. My dear, here the first method, that is using a compound slide. What we do in this method, let me explain you. Okay, let me explain you in this method. Suppose that here we are taking a workpiece. This is a workpiece. This is my initial workpiece, right? This is my initial workpiece. Now what I am going to do here, I will take a tool, right? I will take a tool. This is my tool. I will take a tool. Okay, I will take a tool. Now this is my tool. Now I am going to move the tool. I am going to move the tool. Here, this is what? Let's say this is the axis of rotation of the workpiece. Here, I have given the feed to the tool, not along the axis of rotation. Okay, I have given the tool right in this direction. Let's say this is what? This is X direction and this is what? Y direction. So here the feed of the tool neither in X direction or neither in Y direction. It is in X, Y direction. So compoundly we are giving the feed, right? Compoundly we are giving the feed. So here limited movement of the compound slide, feed is given by basically hand and is non-uniform. This is responsible for low productivity and low surface finish and can be employed for turning a short. It can be used, okay, it can be used for, okay, it can be used because manually given feed, okay, produce a rough surface. So we don't use this type of method over a large cutting length, right? So short internal and external taper, it can be used for short internal and external taper Okay, external taper. Am I clear? With a large angle, with a large angle, with a large angle. Now what do you mean by with a large angle? I will tell you. Don't worry, I will explain each and everything. Right, I will explain each and everything. My dear, suppose that you have produced a taper turning workpiece. Suppose that you have produced a taper turning workpiece. Okay, my dear, this is the initial diameter. Let's say is capital D, and this is the other diameter of the taper turning, that is small d. This is the taper turning length, right? This is what taper turning length, that is what L, right? Now here see, this is the alpha, this angle I am talking about. This angle I am talking about. My dear, from the geometry you can find out that tan alpha equal to what? Capital D minus small d by 2L. So I am talking about this large angle. Alpha should be large here. So basically alpha is known as half cone angle, right? Half taper angle. Half taper angle. Half taper angle, right? Half taper angle. Okay, and capital D is diameter. Capital D is what? Diameter of stock. Diameter of stock, right? Diameter of stock. Small d is what? Small d is small diameter. Small diameter, right? Diameter. L is what? Your turning length, length of taper. Length of taper. Length of taper, my dear. Length of what? Length of taper. Right. So this is the thing. I hope you understand the concept. I hope you understand the concept. Right. Now let's move to the next method, that is a offsetting method. Okay. Actually the question will come, the numerical question will become either in this way, using a compound slide, or offsetting the tail stock. Now let me explain you offsetting the tail stock, because a numerical question will become in this method. There is other method also, like a form tool and the taper turning attachment. In taper turning attachment, generally we use a type of attachment, and by do some setting in that attachment, that by using that some setting in that attachment, you can get a taper surface. Okay. Form tool means a shape of tool is taken, okay, and the cutting will be done by that tool, and the taper surface is going to be what produces. But the question will become offsetting the tail stock. And what is the offsetting of the tail stock? Let me explain you offsetting the tail stock. Offsetting the tail stock. Offsetting the tail stock. Tail stock. Now what we are going to do here, my dear, basically here we take a, basically what we do, there will be a face plate, right? There will be a face plate. In the face plate, you know, there will be a live center. There will be a live center. This is the live center, right? This is the live center. This is a live center. It is supported by lathe dog. It is supported by lathe dog, right? It is supported by lathe dog, and there is a workpiece, right? And here there is a workpiece. Other end of the workpiece is going to attach with the dead center. Okay, this is the dead center. Okay, this is what? This is the dead center, which is attached with the tail stock. Now this is the axis of rotation, my dear. This is the axis of rotation, right? Now, while doing the offsetting, the length of the workpiece should be large. This is the first requirement. The length of the workpiece should be what? Should be large. This is the first requirement, right? This is the first requirement. The length should be, or the length of the workpiece should be large. Now, offsetting the tailstock means I am going to offset the tailstock by a small height. By a small height, my dear student. By a small height, right? By that much height only. That is small h. This is the offsetting the tailstock. Now, this is what your cone angle. That is what? That is the alpha, right? That is what? That is the alpha. Now, suppose that, okay, now by this manner you will get a workpiece. You will get a workpiece. This is the workpiece, my dear student. This is the workpiece you are going to get. See here, this is the taper, right? This is the taper surface. Are you getting? This is the taper surface. So from this side, this is capital D, okay? From this side, this is capital D, and here a small d, a small d. From here to here, this is the taper turning length. This is what? This is the taper turning length, that is small l, and that is what? Capital L, right? So my dear student, listen me carefully. You know that if, okay, you know that from here that tan alpha equal to capital D minus small d divided by 2l, right? Also from here sin alpha, okay, here alpha is very small, here alpha is very, very small. So whether you take a sin alpha, or a tan alpha, okay, or a tan alpha, it will be almost same. It would be almost same. So alpha h by L. So here you can write that h by L equal to capital D minus small d divided by 2L. So this is a offsetting method, right? Again, this is a offsetting method. Am I clear? So this is the thing, alpha is a half cone angle. Again the concept is same. Again the concept is same, right? Now let me solve one question. A shaft of length 90 mm. A shaft of length 90 mm has a taper portion of length 90 mm, that is a capital L. Taper portion, that is a small l. The diameter of the taper is 80 at one end, 65. So it is the capital D and it is a small d at the other end. If the taper is made by tailstock set over method, the taper angle and the set over respectively are. So my dear, the taper angle and set over respectively are. So you can find the h here. H equal to what? Capital D minus small d divided by 2l. See here, divide by 2l into what? Into capital L. Into capital L, right? Into capital L. So this is the thing. Now see, h, capital D is what? That is 80 minus small d, that is what? 65 divided by 2 into L, that is 55. Okay, capital L, that is what? That is 90. Okay, that is 90. That is 90. So are we able to calculate? Yes. 80 minus 65, answer divide by 2 into 55, answer multiply 90, that comes 12 point something. So here 12.272 mm, right? Now my dear, h by L, tan alpha equal to h by L. H is 12.272, right? Divide by L, that is what? Divide by, that is what? 90. He is asking taper, the taper angle. So the taper angle. So answer divided by 90, shift tan inverse answer. It is coming here. It is coming alpha equal to 7.765. Dear It is saying half cone angle, half taper angle, and he is asking the taper angle. So make it twice. It comes 15.5. 2 alpha, that is taper angle 15.53 degree. So 15.53, and A is the correct answer, right? So A is the correct answer. So I hope you understand this concept. Now we are going to start a drilling operation, right? So my dear, in drilling, you have seen that this is a drilling tool. Okay, so in drilling there is a various component which we are going to discuss one by one. So let me discuss the drill tool. Here you can see that in a drilling tool, this portion is known as, right, this portion is known as shank. This is top part of the body, and this is known as what? Shank. This end portion of that shank is known as tang. Basically this tang is going to fix into the drill chuck, right? Now this is what? This is neck. This is the weakest portion of the drill. Suppose if the maximum load comes on a drill, then the drill tool will be going to fail from here, right? Then the drill tool will be fail from here. Now this is the helical fluid of the drill through which cutting chips will comes out and cutting fluid will go inside the machining operation, right? This is the cutting edges, okay, by which we are going to do a machining operation. So this portion is known as body, right? This portion is known as body, and this is the axis of rotation of the drill tool about which the drill is going to be rotate. Now there is some angles. Let me discuss some angles like axial rake angle. Axial rake angle. Before discussing the axial rake angle, I am going to discuss the helix angle. Let me discuss you about the helix angle, right? Let me discuss you first about the helix angle. Look, helix angle is what basically? Let me discuss you the helix angle. Look, this is the helix angle. And what is the helix angle? Let me show you. Let me show you. See, this is the axis of rotation. Is it visible, right? Or here you can see this is the axis of rotation of the drill tool, right? This is the axis of rotation. If it is not visible, I will change the color. I will change the color. See here. This is axis of rotation of the drill tool, right? Similarly here you can see this is the axis of rotation of the drill tool. Now see the outer periphery of the drill tool, that is the outer periphery. Okay, now see what is the angle in between this. This is known as helix angle, right? This is known as helix angle. This is helix angle, and sometimes this helix angle is also called as rake angle. Sometimes we also called as rake angle, right? Sometimes we also called as rake angle. My dear, basically this is the edge of the outer periphery. Here you can see this is the edge of the outer periphery. Here this is the edge of the outer periphery. See here, this is the edge of what? This is the edge of outer periphery. Again see, this is the edge of what? Outer periphery. Again see, this is the edge of what? Outer periphery. Again see, this is the edge of what? Outer periphery. So helix angle is the angle when the outer periphery of the helical fluid, okay, makes an angle with the axis of rotation, that is known as helix angle. My dear, as you know, the fluid is helical. So once it start from its surface, you can see here, this is the axis of rotation. See here, this is what? This is the axis of rotation. See, this is the axis of rotation. If I am right, yes, this is the axis of rotation. See here. Here you can see this is the axis of rotation. From here the helical fluid starts forming. So from here there is no helical surface at the axis of rotation. So here basically I'm talking about the axial rake angle, right? The surface of the helical fluid start from the axis of the drill. So here axial rake angle is 0. Now when you go somewhere else here, right, when you go somewhere else, right, somewhere else, now here the fluid, whatever be the angle is going to make, it is known as axial rake angle. Now this axial rake angle goes vary. Why? Because see here, now this axial rake angle goes vary, right? This axial rake angle goes what? Goes vary, because it is a helical fluid and helical fluid keep changing. When you reach at the periphery, my dear, when you reach at the periphery means like that. So here the axial rake angle become equal to the helix angle. Axial rake angle become to the helix angle, right? So axial rake angle, axial rake angle, axial rake angle, okay, at the center, at the center, at the center, or at axis of rotation, axis of rotation, axis of rotation, axial rake angle at the center or at the axis of rotation is what? Is 0, because there is no helical surface. When you start going away, when you start going away from the axis of rotation, then what happen? A helical fluid start forming, like here. A helical fluid start forming, right? A helical fluid start forming. See, a helical fluid start forming. See, okay. So when the helical fluid start forming, the axial rake angle also start changing or starts making the angle with the axis of rotation, right? And at the periphery, the axial rake angle has its maximum value at the periphery, that is at the edge of the fluid. The axial rake angle is the maximum, it has a maximum value which is equal to helix angle, right? Which is equal to helix angle. So this is the thing, that axial rake angle is the angle between the face and the line parallel to the drill axis at the periphery of the drill. It is equivalent to helix angle, right? It is equivalent to helix angle. A question was asked in the GATE exam. The rake angle in the drill increases from center to periphery, decreases from center to periphery, remain constant, is irrelevant to the drilling operation. So as I told you, at center axial rake angle is 0, and at the periphery it has a maximum value which is equal to the helix angle. So my dear student, here A is the right option, right? Here A is the right option. Now let's talk about the point angle. Point angle is what? Basically here point angle is, I'm talking about point angle. I'm talking about point angle. Basically point angle, what is point angle? Point angle, let's say this is a drill tool. This is the drill this is a drill cutting edge. This is a chisel edge. Now whatever be the angle made by the cutting edges is known as point angle, right? Is known as point angle. Now this point angle will select on the basis of the machining material, right? For the machining material, the point angle is selected suited the hardness and brittleness of the material being drilled. Material being drilled. Material being drilled. Harder the material, have higher point angle, right? Harder the point angle, have higher point angle. Softer the material, have lower point angle. So it's a very important point. It is a very important point. This point is not so important. The second point is very important, that harder the material have high point angle, softer the material have lower point angle. Now the next thing which generally comes in the drilling operation, that is the machining time. My dear student, for that you have to understand few things. Like this is the drill tool. Okay, this is the drill tool. Now the drill tool has a diameter of d, which is rotating with rpm n, that is in revolution per minute, right? That is in revolution per minute. Now if it is rotating, then what will be the cutting velocity? Cutting velocity is perpendicular to the cutting edge, right? Like from this cutting edge, cutting velocity is perpendicular, it is acting towards you. At this cutting edge, the cutting velocity is perpendicular to the cutting edge into the board. So what will be the cutting velocity? Cutting velocity is pi dn by 1000 meter per minute, right? There is one more parameter which we provide, which is that feet, that is in per revolution, right? Per revolution. In one revolution, how much tool is traveling inside the workpiece? Okay, going inside the or going downward, right? My dear, if you multiply f into n, then what it gives? It also gives the velocity. Let's say the velocity going in downward direction, I will say y. Basically this is the tool velocity, right? This is per minute, per minute. Okay, tool velocity, right? Tool velocity, tool which is moving in downward direction. This is tool velocity which is moving in downward direction. This is cutting velocity by which tool is cutting the workpiece. Now let's discuss about the cutting time. Now this formula is little bit clear to you. What is that? That is the cutting velocity is clear. Now I'm going to talk about the machining time. Right, suppose that this is your tool, this is your tool. Now the tool is going to approach toward the workpiece, okay, by length L2, If it is not visible, then I'm going to draw again. Don't worry, I'm going to draw again each and everything. Suppose that this is my workpiece and I have to drill, okay, this much hole, right? Suppose that I have to drill this much hole, and this is the axis of rotation of the drill tool. This is the axis of rotation of the drill tool. This is the axis of rotation of the drill tool, and this is your drill, right? This is your drill, right? This is your drill, and this is C here. See, this is the drill tool. Now drill is not touching toward the workpiece. Here drill is not touching toward the workpiece. So this is the L2 distance, that is the approach distance. The drill has to travel in the downward direction, so that now it is touching. Now this length is known as the workpiece length. Let's say it is L1, right? Let's say it is L1. Suppose that if the drill tool will reach, is going to reach. Now tell me, is the drill is completed? Basically I'm talking about the throw hole. I'm talking about the throw hole, right? I'm talking about the throw hole. I'm talking about the throw hole. I'm talking about the throw hole, my dear, right? Here in case of throw hole, the drill is not completed yet. So the drill tool has to move how much distance? That much distance. And it is known as L3. L3 is a cone height, right? L3 is a cone height. Now the drill is come here. Okay, now the drill comes here, right? By a distance, that is what? L3. But sometime we over travel the drill to ensure that throw hole is completed, right? But sometime we over travel the drill. See here. I'm talking about this. So this distance is L4. This distance is what? Basically L4. So L4 is over travel. So let me write down each and everything. L1 basically length of workpiece. length of workpiece which is going to drill, right? L2 is approach distance, approach, ROACH, approach distance, L3 is cone height, okay, cone height, okay. And what is that? My dear, it is very simple that you know here, see here, this is what? See, this is what? Beta, right? And this is what? D by 2, because the whole angle is what? 2 beta. It is symmetrical, so half of the angle is what? 2 beta. Now, we have to find out this thing. That is cone height. That is what? L3. So, my dear, here 10 beta equal to, see here, 10 beta equal to D by 2 divided by L3. So L3 equal to D by 2 divided by 10 beta, right? So it is D by 2 divided by 10 of beta. Now L4 is over travel distance, over travel. Now the total machining length is, that is L1 plus L2 plus L3 plus L4. Now if the tool is, if you have provided a feed what? F, right? mm per revolution, if you have provided the feed, and the tool is rotating with RPM n revolution per minute, then the tool velocity is F into N, that is represented by what? Let's say Vy. So the machining time, right? Machining time will be what? Machining time will be LT divided by Vy. LT is what? L1 plus L2 plus L3 plus L4, and Vy is what? F into N, right? Now my dear, material removal rate, MRR, it is what? Pi by 4 T square into Vy, that much mm per minute, right? That much mm per minute. So this is a basic thing. Suppose that if you are doing a throw hole, right? Not a throw hole, if you are doing a blind hole. Suppose that if we are doing, if we are producing a blind hole, okay, we are producing a blind hole up to like that, okay. So you may say, sir, if we are going to make a blind hole like that, in that case, this is the machining length basically, right? This is the machining length, if I am not wrong. This is what? This is the machining length, right? So here you can say, sir, this is what basically the machining length, right? This is the total machining length or your machining length. My dear, in that case, what should be the length, okay, of the tool which is going to be travel while machining of length L. Now if the drill tool is going to travel, suppose that the drill is reach here. Suppose that a drill travels here, okay, reach here. So tell me, is that drilling is completed? No, because that much material is still there. So drill is not completed. In that case, the drill has to travel up to that distance. My dear, right? This drill is what? A hole which is symmetrical about the axis, a cylindrical hole. So in that case, this is basically what? This is a L3, and this will be the total machining length. this will be the total machining length, right? So the total machining length, I'm talking about the blind hole. I'm talking about the blind hole, right? I'm talking about the blind hole. So machining time, again, machining time is what? Total machining length divided by what? F into N if drill is rotating with the RPM N and having a downward feed F, right? So this is the case of blind hole. Most of the question, examiner is not going to mention whether it is a through hole and blind hole. If he is not going to mention, okay, which type of hole is that, you have to take a through hole, right? You have to take a through hole. So I hope things are very clear to you, right? Things are very clear to you. Let's discuss some question. Let's discuss some question regarding this so you will understand. Look, examiner has mentioned through hole of 10 mm diameter are to be drilled in a steel plate of thickness 20 mm thickness. Drill spindle speed is 300 rpm, feed is 0.2 mm and drill point angle 120. Assume drill over travel 2 mm. Okay, the time for producing a hole will be, look, he hasn't mentioned the, please remember what I am saying, he hasn't mentioned the approach distance, right? He hasn't mentioned that approach distance. He mentioned what? The thickness of the plate, that is L1. He mentioned the over travel, means L3 also comes. So neglect L2 if it is not given in the question. So in LT, L1 is given to us, L2 is not given, so neglect it. L3, it is given indirectly, plus L4 over travel is given to us. So my dear, L1 is what? L1 is 20, right? L1 is 20, L2 is 0, L3 is what? D by 2 diameter, through hole 10 mm diameter, D by 2 10 by 2, that is 5, divide by 10 of beta that is 60, right? Plus L4 that is what? 2. Now this is your total travel distance, right? This is your total travel distance. So it comes 20 plus 2, answer plus 5 divided by 10 of 60, right? So it is 24.8867 mm, right? Now the machining time is that, machining time is total length divided by what? Vy. So here RPM is given to us, feed is given, but RPM is given. So LT, that is 24.8867 divided by Vy, that is 0.2 into N, that is 300, right? So answer divided by 0.2 into 300, okay, answer into 60. So 24 point, here my answer is coming, machining time is coming 24.8688886. So approximately 25 second. Approximately 25 second. B is the correct answer, right? B is the correct answer. Now the next question is that a single pass drilling operation, a through hole of 15 mm diameter. So diameter is given to us, that is D. Drill in a steel plate of 50 mm thickness, that is L1. Drill spindle speed RPM, so N is given, feed is given, that is F, and drill point angle, that is 2 beta is given, 2 beta, that is a point angle is given, assuming 2 mm clearance at approach and exit. Okay, so this is given, and the total drill time, you have to find the total drill time. So my dear, here total machining time will be 2 mm approach, 2. Okay, now how much thickness? That is 50 mm thickness, so 50 plus cone height, so it will be cone height. How much be the diameter? D by 2, 10 beta, so D by 2. Okay, cone height will be what? 7.5 divided by 10, 59. 7.5 divided by 10 of 59. Okay, plus approach angle, approach distance, exit is what? Again 2. Exit is what? Again 2. He is mentioning now, assuming 2 mm clearance at approach and exit. So this is the total time. So what will be the total length? 2 2 and 2, 20, 54. 54 plus 7.5, 10 of what? 59. So 54, 7.5 divided by 10 of 59, it is coming answer plus 54, it is coming 58.506, right? mm. You have to find the machining time. Machining time is 58.506. Now divide by f. F is what? F is 0.2. N is what? N is 500. 0.2 and 500. Okay, 0.2 and 500. 0.2 and 500. Right? F into N. So answer divide by 0.2 into 500. So it is coming answer into 60. It is coming 35. It is coming 35.103 second. Right? This is the correct answer. So 35, that is option A is the right one. Right? Now let's see the next question. This question comes from a blind hole. Blind hole, 10 mm diameter, that is D, 50 mm deep, that is L, are being drilled in a steel block. Drill spindle speed is given, that is N. Okay, feed is given F, point angle is given, that is 2 beta, and machining time per hole. So you have to tell me machining time. I told you to find out the total length, that is what? L plus D by 2, 10 of what? 60. So L is what? L is what? That is 50. D is what? 10. So 5 by 10, 60. 10, 60. Right? 5 by 10, 60. Here 5 divided by 10 of 60. Answer plus 50. 52.886 mm. Oh, sorry. Yes, mm. Right, mm. Now the machining time is 52.886. Divide by F into M. Divide by feet, that is 0.2. Right, 0.2 into 0.2. My dear, here maybe you have surprised that sir has written 35 point. Here answer will comes in minute, but I have multiplied with 60. That's why I am getting 35.103 second. Right. Here also I am doing the same thing. LT divided by what? F into N. N is what? RPM. RPM is what? 600. So here also I am getting what? In minute. Right. So answer divided by 0.2 into what? 600. It is coming 0.44. 0.44 minute. So 0.44 minute is coming. So this is the time to produce one hole. Now how many hole you are producing? Basically it is given in the next question. Suppose that this data is same. Okay, now you are producing 200 holes by this tool. So you are producing 200 hole, means if you multiply machining time into 200 hole, then you will get what? Tool life. So it will be what? Answer into 200. So the tool life will be what, my dear? 88.144 minute. This will be the what? This will be the tool life per tool, or you can say that much minute per tool. Okay, that a single tool is going to produce 200 tool and will consume 88.144 minutes. Right. Now Taylor's tool life equation is given Vt to the power 0.3 equal to C. You have to find the C value. We have to find the C value, my dear. Okay, then let's find the value of C. Now V, that is the cutting velocity, is what? Pi d n divided by what? 1000. Right. Tool life is what? 88.144. Okay, V. So pi. D is what? Diameter. Diameter is what? Diameter is 10 mm. Blind hole 10 mm diameter, and n is what? 600. So pi d. D, that is 10. 600 divide by what? Divide by 1000. V into T, that is what? 88.144 to the power 0.3. This will give you the value of C. So answer to the power 0.3. Answer into shift pi into 10 into 600. Answer divide by 1000. It comes C comes 72.25. Let me see, 72.25. So B is the correct answer, right? So my dear, thank you very much for watching this session.